Hey everyone, how are y'all doing today? Good to hear, good to hear. So today we are doing an exam review. Okay, a little bit. So first, a bit about the exams. I'll send out an email on this after class, but so the way, hang on, situate this real quick. Alrighty, so the way these are going to work is, so tomorrow in Canvas, you will take your exam, and there are going to be, so 3 time slots. So there will be, so Eastern time, these are all Eastern time. They'll be from 10 a.m. to 12 to noon. 6 p.m. to 8 p.m. and then 8 p.m. to 10 p.m. Don't know why those weren't spaced out more, but those are the slots. So you have a 2-hour time slot in which you can, so 3 2-hour time slots in which you can take your exam. There's a different version for each one, but they're all rather similar. And the exam is going to be an hour long. So you have 1 hour inside those 2-hour time slots to take it. So you want to make sure to start with at least an hour left, because so if you do say the 6 to 8 p.m. slot and you start your exam at 7:15, it's still going to end at 8 o'clock, regardless of whether or not your hour is up. So you want to give yourself, you want to start at least 7 o'clock because the exam is going to close at 8, that time slot. But you have an hour to do your exam, as long as you give yourself enough time. So after that, so you're just going to, just a sec. Make sure there are no multiple choice here. Okay, so most of, sorry, go ahead. Correct. So it's going to be like midterm 1A, midterm 1B, midterm 1C, that kind of thing. I need to go ahead and import those. I don't know exactly what they're called, but it's going to be something like that. And like the A time slot will be the early 10 to noon. The B will be 6 to 8. The C will be 8 to 10.
Okay, perfect.
Sorry, go ahead.
Could I ask you a quick question?
Sure.
Okay, so with the exam, right, if I were to log in at 8 p.m., is there like right, you said there's 1A, 1B, 1C, let's call C at 8 p.m. to 10 p.m. Yes. I would just get onto Canvas and log in, and that's all I'd have to do, right? Just take it within that time.
Right. So it's going to be under quizzes in Canvas. And it's going to be just like if you've ever taken a Canvas quiz, it's going to be similar to that. You log in, you start, and then you will have an hour. But yeah, so it won't be available. Like the one you want won't be available until the given time slot. Right. So if you want to do the 6 to 8 one, that's not going to be available until 6 to 8, obviously, if that makes sense. But yeah. So after you do that, so then you just submit that. I don't believe you type in very much. There might be like one multiple choice or something like that for that. But then you go to the upload file or the upload assignment, and you'll take a you'll make a PDF of your work, and you will upload your work. And you're going to want to do that within 10 minutes of finishing your exam. I will import that. In fact, let me go ahead and do that now. And in the meantime, we can discuss whatever problems you'll want to look at. Will there be? Yes, correct, Saeed. Yeah, there will. So I'm gonna go ahead and import this. I'm going to assume for the time being that it was like it was last semester, but I'm gonna import it and take a quick peek at it when it's done importing, and then I will confirm that it is indeed, or tell you if it is otherwise. So what exam or what midterm practice questions would we like to? Yes, I'm importing them right now. So you will be able to see them in a matter of a couple minutes. Okay, so it's if you want to ask some of the review questions. Oh, so wait, the one in Canvas, right? Okay. Are you requesting a problem, Saeed? Okay, so which one specifically do you want to look at? Okay. Number 3? Okay, sure. All right. All right, so we're looking at problem number 3 from the exam review questions on Canvas. Okay. So the first 3 problems. Is that what you were saying, Saeed? Well, we'll do number 3 first while you clarify. Okay, so number 3, part A, is we're given 2 lines and we want to show that they intersect. So 3 plus t, 4 minus 2t, and 1 plus t is 1 line. And then we have 2 minus 3t 1 plus t, and 2 minus t. So we have these two lines we want to show they intersect. Well, we have limited time. So I will be continuing this for probably an hour and a bit after the normal end of class. And then I'll have office hours later. But we still have not enough time probably to do every single problem. So I'd rather do specific ones that you would like to look at. Okay, so we want to show these two lines intersect. So two lines intersect. So they intersect. We'll call this. We'll call this first guy R1 of t, and the second guy R2 of t. Okay, so R1 of t is the first line, R2 of t is the second line. So we need two different, so if they intersect, that means that they share a point, and that means that there's some time t1 where we're at this shared point on the first line, and a possibly separate time t2 where we're at that point on the second line, but they don't have to be the same time. That would be particles collide if they're at the same point at the same time. But if they just intersect the paths, then it could be two different times. So we need a t1 and a t2 such that R1 at time t1, the particle on R given by R1 is at the same point as the particle given by R2 is at some different time t2. So we equate, so if we have two vectors that are equal, that means their components are equal. So each component is a separate equation. So for the first component, we have 3 plus t1 is time t1, first component of R1. That's equal to the first component of R2 at time t2, which is 2 minus 3 t2. And then we do the same for the second component. So 4 minus 2 t1 equals 1 plus t2. And then we equate the third components. 1 plus t1 equals 2 minus t2. So we need to find a t1 and a t2 which satisfy all three of these at the same time. So what we do is we just pick two of them. So we have two unknowns, but three equations. So if we can solve two equations and two unknowns for t1 and t2, and then we plug that t1 and t2 into the third equation to make sure that that t1 and t2 satisfies that as well. It should, because we're showing that they intersect, but that's how we do it. Okay, so solving the first two equations, just get rid of one of the variables. So let's multiply the first equation by 2, and then add the first two equations together to get rid of t1. So we get 6 plus t1 equals 6 minus 4 t2. sorry, 4 minus 6 T2. That is important. Let me move a little quickly here. I'm dragging my feet a little bit. And then 4 minus 2T1. Whoops, sorry, 6 plus 2T1. Okay. That is equal to 1 plus T2. So add the two equations together. We get 10. 2T1 and minus 2T1 cancel, equals 5 minus 5T2. So subtract 5 from both sides. We get 5 is equal to negative 5T2. So T2 must be equal to negative 1. So if T2 is equal to negative 1, we'll just plug into one of the equations. Let's say plug it back into this guy. So we get plugging in T2 equals negative 1. So we get 4 minus 2T1 equals 1 minus 1, 0. So T1 is equal to 2. Okay, so we found a T1 and a T2, which satisfy the first two equations. T1 equals 2, T2 equals negative 1. And so then we plug this into the third equation and make sure it satisfies the equation. If it satisfies the equation, then that means the lines intersect, right? They share a point. At time T1, we get the same point on the first line as we get at time T2 on the second. So plugging these guys in, we get, so 1 plus 2, which we got for T1, is equal to 2 minus negative 1. That is indeed true. So the lines intersect. Oops. Oh my goodness. Okay. So any questions about part A? Okay. Why do you have T1 and T2? It's because, okay, so if we have a parameterization of lines, so think of a parameterization of a line as giving you a particle moving along a line at a given time. All right, so for this first one, if you plug in a time t into the first equation, that's going to give you a point on the line where your particle is at that time t. So if the two lines intersect, that means at some time on the first line, your particle is going to be at this point here. And at some different time, the particle on the second line is going to be at that same point if they intersect. So the particles don't have to be at the same point at the same time, but the line, the path the particles take, if they intersect, then there's some time T1 where we're at this point on the first line and some possibly different time T2 where we're at that same point. Does that make sense? So think of T as giving time, and R1 of T gives you your position at time T, and R2 of T gives your position at time T. Okay, so part B. So find the acute angle, and need to be careful. So we want the acute angle of their intersection. And note, whoops, go away. Beautiful. God damn it. The acute angle of the intersection. So note that there are two angles we could say that the lines make, right? We could say they make this acute angle here or this bigger guy here. We want the smaller of the two angles. We talked about this a bit before, but let's remind ourselves how this works. Okay. So how do we find the angle between two lines? What do we need to look at? Well, let's say this is L1 and this is L2. So L1 is going to have a parallel vector, V1. And L2 is going to have, it's also a parallel vector. We'll say it's this guy, whatever, V2. And the angle between the lines is going to be related to the angle between those vectors. But notice the angle between the vectors could be obtuse. So the first line is going to be parallel to what vector? So R1 of t. What's the direction vector for that guy? For this guy here. So 1, -2, 1, right. So 1, -2, 1. And line 2 is going to be parallel to, similarly, -3, 1, -1. Right? Yes. Okay. Okay. So we know cosine of the angle between two vectors is going to be the dot product of the two vectors. You know what? Let me call this guy. That's fine. That's fine. So 1, -2, 1 dot -3, 1, -1 divided by their magnitudes. So magnitude 1, -2, 1 times magnitude -3, 1, -1. Okay, but this could be obtuse, right? If your dot product is negative, that indicates that the angle between two vectors is obtuse. If the dot product is positive, that indicates that the angle between the two vectors is acute. But if we just take the absolute value of the dot product, then that's going to give us cosine of the acute angle between the two lines. So I'll briefly explain the reason. If you don't understand it, that's okay. Just remember that if you're finding the acute angle between two lines, you need to take the absolute value of the dot product. But the reason for that is if the angle is obtuse, if the dot product's negative, then if you say take, instead of V2, you take negative V2, then that's still parallel to your line. And the angle between negative V2 and V1 is that acute angle you want. And So if you change the sign of your vector and dot it with it, it's going to go from negative whatever it was to positive whatever the dot product is. In other words, you took the absolute value. So that's what taking the absolute value is doing there. Okay, so we take the dot product, we get -3 minus 2, so -5 minus 1. So that's absolute value -6. You could, but don't say 180, say pi. So erase degrees from your mind entirely for this class. But you could do that. You could do that. And that would also be correct, yes. Divided by, so magnitude of 1, -2, 1 is square root 1 plus 4 plus 1, so root 6. And then magnitude -3, 1, 1 is square root of 9 plus 1 plus 1, so root 12. And so you could leave it like this, but we can simplify, and we're actually going to get a nice value. So root 6, or absolute value of -6 is 6. Square root 6, so square root 12 is square root 6 times square root 2. And square root 6 times square root 6 is just 6. Those are going to cancel. And so we get 1 over root 2, which is a nice value because we know an exact angle, theta, which when we take the cosine, we get 1 over root 2.
I think it should be square root 11.
Square root 11? You're absolutely right. I got a little excited there. Yep, you're right. Just keeping you all on your toes. Okay, times root 11. Well, that's unfortunate. That's fine though, not a problem. So we get 6 over square root 6 times square root 11, which is just root 66. Can't really simplify that. Well, doesn't matter. Doesn't matter. So theta would be cos inverse root 66. Yes. And that's the exact angle there. Yeah. Alternately, as was mentioned before, if you get a negative for the dot product, we know that we're getting an obtuse angle, and the angle we want is actually pi minus that. So you could say, or pi minus cos inverse -6 over root 66, but I wouldn't. Those are both correct. But I would just remember to take the absolute value. So where does the 6 go? Which 6? The root 6 on the bottom? I just multiplied root 6 times root 11. If that's what you're asking.
Like when you have 6 over square root of 66, why wouldn't it be inverse cosine of 6 over square root of 66?
Oh, it is. It is. I think I said it out loud, but didn't write it down. My apologies. My apologies. Yes, you're right. You're right. I wrote it down wrong for some reason. Yep. Yep. That is. Thank you. Okay. And then part C. So find the equation of the line through the point of intersection which is perpendicular to both lines. Okay, so original two lines, we know they intersect. We want the line which goes through that point of intersection, which is perpendicular to both of those two original lines. So what two things do we need for the equation of a line? So we want the equation of some line. What two things do we need to define the equation of a line? Yeah, you're thinking the right thing, but I would not call it slope. Right, so we need a point and not a normal vector. We need a normal vector for a plane. We need a parallel vector. So we need a point. And we need a parallel direction or a parallel vector. Let me say parallel direction vector. How about that? Okay, so the point we know is the point of intersection. So we proved that the two lines intersected by finding a T1 and a T2, where we're at the point of intersection at T1 on the first line and at the point of intersection at T2 on the second line. But we didn't give a point exactly. But we can easily get it from the times T1 and T2 that we found. So R1 of T1 is going to give us the point on the first one, and R2 of T2 is going to give us that same point. So it's going to be the point of intersection, which is R1 of T1 or R2 of T2, doesn't matter because they're going to give the same point. Which is, okay, so T1 was 2. So 3 plus 2 is 5. 4 minus 4 is 0. 1 plus 2 is 3. So 5, 0, 3 is our point of intersection. So technically, when you plug them into the vector equations, you get a vector, but it's the vector, the position vector for this point. Like, it's not a huge deal if you write a vector there, just make sure. And when we plug it into the second, -1, just to check. So T2 is -1, we get 5, 0, 3. Again, exactly the same point. So that's our point of intersection, which is the point we know is on our line. Okay, well, what about the direction of our line? What do we know about this line that we wanted to find? Well, we know it's perpendicular to the other two lines. So how do we find a vector which is perpendicular to two lines? What do we need to do? Little more complicated than that because there's a simpler way to do it, basically. So if we have two vectors, right, the direction vectors of each of these lines, the v1 and the v2, and we want to find a third vector which is perpendicular to both, we take their cross product, right? So we take the cross product of the direction vectors of our lines, which we said were 1, -2, 1, and -3, 1, -1. -3, 1, -1. And when we take the cross product, whatever, I'll just write it out real quick. We get the vector 1, -2, and then 7. Nope, -5. So -3 plus 1. Yep. Yep. Okay. So we have our point and our parallel vector. Just going to give myself some room here. And so we put those two together. So you could write it in scalar parametric form, or you could write it in vector form. So in scalar parametric form, we get x is 5 plus 1 times t, so 5 plus t. Y is 0 minus 2t. And z is 3 minus 5t. Oops. Or you could write it as, in vector form, x is 5 plus t, y is -2t, and z is 3 minus 5t. Both are fine. Or 503 plus t times 1, -2, -5. Okay. Any questions about that one? I spent far longer on that than I wanted to. Okay. Yes. Sure. Okay. Tyler, are you talking about the are you talking about the one on Canvas? Because those have been posted for a few days, the solutions, or for a couple days, I believe. I don't have those, and I don't think the course coordinator does either. So my apologies about that. But I would do the exam on the Canvas questions first. And if you have time, then do those ones. Yeah, I don't have those, unfortunately. Yeah. Okay. So let's do number 2 because we'll do 2 then 1. Doesn't really matter, but I figure more people will be here to see number 2, and 2 is kind of a little different. Okay, give a parameterization of the line which goes through a couple points. Actually, it's not too bad, but so give a parameterization of the line through the points 1, 4, 2. That's supposed to be 2. and 205. Okay, so this one's not too bad. So we'll say the first guy's P and the second guy's Q, right? So what two things? We need the equation of a line. So once again, the two things we need for the equation of a line are a point and a parallel direction. So our point, you can pick either P or Q, doesn't matter. Let's say P is fine. That's a point. And for a parallel direction, let's just take the vector from P to Q. We know that's got to be parallel to our line because both points lie on the line. And our vector from P to Q is just subtract coordinate by coordinate. So end at 2, start at 1. So that's 2 minus 1, which is 1. The second component is 0 minus 4, which is negative 4. And the third is 5 minus 2, which is 3. So our parameterization is going to be, so our point 1, 4, 2 plus t times our direction 1, negative 4, 3. That's fine to leave it like that, but I'm just going to put it together. So we get 1 plus t, 4 minus 4t, and then 2 plus 3t. Okay, so that's our line through 2 points. Simple enough. So B so if point A where is the point of intersection of this line we just defined with the xy plane, and B is the point of intersection with the yz plane, find the distance from A to B. Okay. So we have a line and we're looking at the point where it intersects the xy plane, or the point where it intersects a couple different planes. So a couple points of intersection. So we want to find out where our line intersects the xy plane. Well, what's the equation of the xy plane? Because I'm going to need the equation of this plane to do this. It's the plane z equals 0, right? So R of t was our line. So for which value of t at what time is the third component, or let me say the z component, of our parameterization So when is the third component of our parameterization 0? At what time t? So remember, let's remind ourselves. So r of t, we said was 1 plus t, 4 minus 4t, and 2 plus 3t. Okay, so we set the third component, which gives us the z coordinate, equal to 0. And they couldn't give us a nice number, of course. So we see that this happens when t is equal to negative 2/3. Right, we just solve for t there. So then plugging in t equals negative 2/3 into r gives us the point in the xy plane where it intersects. So 1 minus 2/3 is 1/3. 4 minus 4 times 2/3 is going to be 4/3. Nope. So sorry, 4 plus 8/3. 4 plus 8/3 is going to be 16/3. And z is 0. So that's a point. Technically, that's a vector. So the point it intersects is at 1/3, 16/3, 0. Not our final answer, but that is A. Okay. That's a point A. And then we do the same for the YZ plane. So our YZ plane is, of course, the plane x equals 0. Isn't it 20/3? Yes. I'm on fire today, you guys. Holy crap. Awesome. 20/3. You guys are on it, though. Good job. Okay, we do the same thing. We want to find the value of t where x equals 0, then plug that t in to get the intersection with the YZ plane. So t is equal to -1. Right, so we plug, so we set the first component equal to 0. And we get t equals -1. And so when we plug in that time, that gives us our point of intersection. So we get 0, 4 minus 4 times -1, so 8. And then 2 minus 3, which is -1. So B is going to be the 0.08 -1. So we're going to find the distance between these 2 points. Just use the distance formula. The distance from A to B is just going to be the square root. So A was 1/3, 20/3, 0. So 1/3 squared plus 8 minus 20/3, which is 4/3. Wait. No. So this actually was. I was actually right. Right? Yeah. So this is indeed 16/3. Because 4 would be 12/3. So 12/3 plus 4/3 would be 16/3. Okay, so we get 24 minus 16 would be 8 over 3. Squared plus -1 minus 0. Right, so we get 1 over 9 plus 64 plus, we'll just call this 3 over 3, 9. So 10, 74. Yep. So it should be root 74 over 3. Let me make sure. Wait, okay, sorry. 8 is 24 over 3. Wait, was I wrong? Oh, it's 2/3, right? Okay. Nope. Sorry, you were actually right. This is 20 over 3. I was doing plus 4/3, not plus 8/3. Yep. Okay. Right. So that's 26. Okay. Yep. Sorry. Small algebraic error. Okay. So that is number 2. Any questions about that one? Trying to move along a little quickly here. Okay. All right. So number 1. So give a parameterization of the line. Which goes through the point 132, and which is parallel to 4 minus 3t, 2 plus t, 1 plus 3t, which is a line. Okay. So this is part A. So of course, we want the equation of a line, so we need 2 things, a point and a parallel direction vector. So a point, well, we're given, that's 132. And the direction vector, well, we know it's parallel to a given line, so we can just use the same direction vector from that guy. And that is -3, 1, 3. And so we just put these together and we get, so one minus 3t, 3 plus 1 times t, and then 2 plus 3t. Easy peasy, that should be a 2-second problem for you. Okay, so now part B, let's find the equation of the plane which contains both lines. All right, So what two things do we need for the equation of a plane? Right, we need a point on the plane and we need a normal vector. Whoa. So we need a point and we need a normal vector. Okay, so we know two lines, two entire lines on this guy. So we can use any point on either one of the lines. Well, we know a point on the line we just defined there, 1, 3, 2, so let's use that. And if we want the equation of a plane containing two lines, normally what we do is we take the cross product of the direction vectors of those lines. But in this case, what do we know is going to happen when we take the cross product of these direction vectors? We're going to get the zero vector because those two direction vectors are parallel. In fact, they're the same direction vector. So that's not going to give us a normal vector for our plane. So we need to find a different vector which is parallel to our plane, but not parallel to the direction vector of each line, which is the same. So we'll say this is V. That's the guy we know. Oh my God, my dog is going nuts, dude. How do we find a vector which is not parallel to V, but which we know is parallel to our plane? And then we can take the cross product of that vector with V. How can we take these two lines and get a vector not parallel to either line? Right, so what we can do is just find a point on one line. Let's say this is P. I don't know, we'll call this guy P. 1, 3, 2. We know that is on the line we just defined. And let's find some other point on the other line. Let's call it Q, right? And so the vector from P to Q, clearly not parallel to either line, because one point lies on one line, the other lies on the other line. So we know P is 1, 3, 2, the point on the line we defined. We just need to find a point on the other line. Well, you can put in any value of T into the equation of the other line. Just put in T equals 0. We get the point 4, 2, 1 on the other line. So let's say Q is 4, 2, 1. So in this case, P, we already said was 1, 3, 2. Q is 4, 2, 1, or whatever you want. It doesn't matter. It'll still work. So the vector from P to Q is going to be 4 minus 1, which is 3, 2 minus 3, which is negative 1, and then 1 minus 2, which is negative 1. So we're going to let our normal vector be the direction vector cross this other vector PQ. And we know that's going to be a normal vector because V is parallel to our plane and PQ is parallel to our plane. right? Because both points lie in the plane. But they're not going to be parallel to each other, so we're not going to get the zero vector when we take the cross product. So V we said was -313. Q is 3, -1, -1. And that is going to be 2. So 9 minus 3 is 6. And we're going to get 3 minus 3 is 0. So V is just the direction vector of both of these lines. This -3, 1, 3. So what we want to do is we want to get two vectors. So if we want to find a normal vector to our plane, we find two vectors parallel to our plane and take the cross product. And we can't take the cross product of direction vectors with the two lines because they're parallel, and that gives us a zero vector, which is not going to be a normal vector. So we're fine with -3, 1, 3, but we need to find some other vector, and that's where we get this PQ. That's why we get this 0.1 P on one line and Q on the other line. The vector from the other two is going to be parallel to our plane, but not parallel to either line. Okay. So we get our normal vector is 2, 6, 0. And so we just plug this into the equation of the plane. So we get 2 x minus 1 plus 6 y minus 3 plus, I mean, you don't need to write this down, but it's 0 times z minus 2, which is, of course, 0, equals 0. It is not. No, it would be 260. Because remember, you do the plus minus plus thing. So it'd be -j times 3 minus 9. Yeah. I didn't write it in there in the interest of time, but yeah, you got to remember that. And so we get 2x minus 1 plus 6, y minus 3. And depending on the point you pick, or you know, the cross product you do, you could get, say, instead of 260, you could get -2, -60, or 130, or any multiple of that, whatever. But yeah, I don't want to spend too long on that. But any questions about that? Number 1. Yeah. Okay. No, let's do number 6 because I did not explicitly cover this semester, and I want to make sure everyone knows how to do this. Okay. So number 6. So part A. So we're going to find the equation of the plane, which is parallel to the plane 3x, sorry, no. Parallel to the plane, yeah, oh no, that was right. 3x plus y minus 4z equals 5, and goes through the point the origin. Yeah. Okay. So as always, we're finding the equation of a plane. So we need a point on the plane and a normal vector to the plane. So a point, well, we know it goes through the origin, which is 0, 0, 0. So that's a point on our plane. And we know it's parallel to this plane, 3x plus y minus 4z equals 5. So if two planes are parallel, their normal vectors are going to be parallel. In particular, a normal vector for one plane is also a normal vector to a parallel plane, right? So what's the normal vector to this parallel plane? So it's going to be 3, 1, negative 4, right? Okay, so we got our equation is 3 x minus 0 plus 4 y minus 0. Oh, sorry, no. Sorry. So plus 1 times y minus 0 minus 4 z minus 0 equals 0. Or in other words, 3x plus, why do I keep writing plus 4y? Plus y minus 4z equals 0. Okay, so that's the easy part. Everyone should know how to do that. Part B, we need to find the distance between the two planes. Which the book does not explicitly talk about. This one doesn't, at least. So I want to make sure everyone knows how to do this. Okay, so if two planes are parallel, they never intersect, and we can define a distance between the two. Okay, so we have two parallel planes. We want to find the distance between the two. What you want to do is basically, the distance between two planes is if you pick any point on one plane, you find the closest point on the other plane, and you look at the distance between the two. It doesn't matter which point you pick on the first plane. If you find the distance to the closest point on the second plane, you're always going to get that same distance. So it turns out that this distance, this other point you find, is if you look at the line through these guys, you could use a geometric argument to show that the line between the two closest points is going to be perpendicular to both planes. In other words, this line is going to be parallel to the normal vector. So we'll say this is a point P on our first plane, and Q is a point on the second plane. Which is closest to point P. So you pick a point on the first one. We're going to pick 0, 0, 0, so we'll see. Actually, it doesn't really, but That'll make our lives easier. So if Q on the other plane is the closest point to this guy, then the vector from P to Q is going to be parallel to the normal vector of these guys. The normal vector of the plane. So what we're going to do is basically we are just going to find any point let's call it, let me make this guy a little bigger. Hang on. Okay. we can find any point let's call it R, actually. We can find any point R on the second plane. Look at the vector from P to R. Project it onto the normal vector. And then look at the length of that guy. So you find you pick some point on your first plane. We're going to use 0, 0, 0. Then you're going to find any point on the second plane. We'll call that R. And we're going to look at the magnitude of the projection, which is just going to be the absolute value of the scalar component of the vector PR onto our normal vector. So that's going to be the absolute value of this vector PR dot n divided by the magnitude of n. Okay, so I kind of a lot going on here, but does everyone sort of understand what we're doing here? So we're picking a point, P. It's going to be 0, 0, 0 in this case on one plane. And we're looking at the distance to the closest point on the second plane. Well, we don't necessarily know what that point is. You could find it, but we don't necessarily know what it is. But we do know that the vector from P to Q is parallel to a vector n. And so what we do is we find any point R on the plane, we project onto the vector PQ. And then when we do that, we actually get the vector from P to Q when we project on there. Well, we don't know what Q is, but we know it's parallel to N. So the projection onto PQ is actually the same as the projection onto N, which is why we did this whole projection business. Because N and PQ are parallel, so the lines through each are parallel. So projecting PR onto PQ is the same as projecting onto N. So we find any line, any point R on the second plane and project PR onto our normal vector, and then look at the magnitude of that guy. And that's just going to be the absolute value of the component of the projection. Okay. I will give you, no, I think I'm not going to. I think I'm not going to do that. So let P be a point on the first line. How do we find n? We already found n, right? Sorry, n is a normal vector, if that wasn't clear. Yeah. Okay, so we're going to let P be a point on the first plane. That's 0, 0, 0. So that's a point on one plane that we know. And then we find a point on the other plane. Well, we don't immediately know. We just have the equation of the plane. It doesn't tell us a point, but we can find a point from that. So R can be any point on the plane 3x plus y minus 4z equals 5. And there's an easy way to do this. You set two of the variables equal to 0, solve for the other one, and you get a point, which lies on that plane. So you could set y and z equal to 0, solve for x, or x and z equal to 0, solve for y, or x and y equal to 0, solve for z. The simplest thing to do here is to set y and z equal to 0. And then we get y equals 5. I mean, you could do the others, but you get fractions, and I like to avoid fractions wherever possible. So we'll let R be x is 0. We set x and z equal to 0, then we get y equals 5. And that's going to be a point on the second plane. So this guy's on our plane, which we just defined, 3x plus y minus 4z equals 0. And the second guy is a point on our second plane. So the vector from P to R is just going to be, of course, 0, 5, 0. Point. Vector from 0, 0, 0 to 0, 5, 0. N is going to be our normal vector, 3, 1, negative 4. And so the distance between the two planes is going to be the absolute value of 0, 5, 0 dot our normal vector, 3, 1, negative 4, divided by the magnitude of the normal vector, 3, 1, negative 4. So just so we're clear, this is going to be absolute value of the dot product of the vector PR and the normal vector divided by the magnitude of the normal vector. So 0, 5, 0 dot 3, 1, negative 4 is going to be 5. So the absolute value of 5, which is just 5, over magnitude 3, 1, 4, which is square root 24. Well, absolute value of 5 is 5. So we get 5 over root 24. Let me make sure. Wait. No, 26. Sorry. Once again, man. On it. Roll, dude. 5 over root 26. Math is hard. So you could memorize the formula, but it's good to understand where the formula comes from because that's going to make it a lot easier to remember that formula. But does anyone need more explanation on the process? how we got to that formula. Okay, if not, go ahead and give me another problem you would like me to work out, and I'm gonna grab some water really, really quick. Five A, all right. Okay, right. So 5A, we have two intersecting planes, and we need to find the equation for the line of intersection. So the line of intersection of the planes. X plus 3y minus z equals 2. And 2x minus y plus 2z equals 5. Okay. So first things first, we're finding the equation of a line. And as we said a million times, the two things we need for the equation of a line are a point on that line and a parallel direction. So some parallel vector. Okay. So for point and direction. So suppose we have, I'm going to do my best here to draw two intersecting planes. Okay, so use your imagination. So pretend those are two non-parallel planes, right? So we'll call this guy big P1, big P2. So these are two planes. So they're going to intersect in a line. And that line of intersection, well, what does it mean to intersect? Well, it means you share points on both planes, right? So the line of intersection is going to lie on both planes. Well, what do we know about these planes? Well, whoops, we know in particular the normal vectors to the planes. Let me draw this at a different angle. Why are you like this? Okay, so we'll say this is the normal vector to the first plane. And we'll say this is the normal vector to the second plane. And because it got erased for some reason, this is the line of intersection. So line of intersection lies in both planes. Okay. So let's start with the direction, the parallel direction of our line. So we'll say V is a parallel vector to our line. Well, we know this line lies in both planes. So the line is going to be parallel to plane 1, and it's also going to be parallel to plane 2. Right, does everyone agree with me there? Of course, right, because it lies in both planes, right? So the line's going to be parallel to the first plane, it's going to be parallel to the second plane. And so what is the relationship between the line and the normal vector from the first plane? So what's the angle between our line and our normal vector? They're going to be orthogonal, right? Because it's parallel to the first plane, so it's going to be orthogonal to the normal vector. Similarly, since it lies in the second plane, it's also going to be orthogonal to the second normal vector. So we know the direction of our line is orthogonal to the first plane, the normal to the first plane, and the normal to the second plane. And so if we take the cross product of the two normals, we're going to get something parallel to our line, right? Because the line is orthogonal to both of those two vectors. So we're going to let the direction be the cross product of the two normal vectors. Well, the normal vector for the first one is just 1, 3, -1. And the normal vector for the second is going to be 2, -1, 2. And when we take the cross product, we get 5, -4, -7. Okay. Let me give myself space here. Let's put the point down here. So that's our direction. Now we need to find a point on our line. So we're finding a point on our line. And so what we're doing is we're finding a point which lies on plane 1 and also on plane 2, right? The line is a set of all points which are shared by both planes. So we just need to find one point which lies on both of them. Whoops. So find one point on both planes. And so just to draw another picture here, so suppose, forget about the planes, but suppose we have, this is our line that we're trying to find. So as long as this line is not parallel to any of the coordinate planes, it's going to intersect each of the coordinate planes somewhere. So in particular, it's going to intersect the plane z equals 0 somewhere. At some point, we don't know what x is, we don't know what y is, but we know z is equal to 0. So we can solve for that. So this is as long as the line is not parallel to z equals 0. This line is not going to be. So you don't need to worry about that. But yeah. OK, so basically you just set one of the coordinates equal to 0 and then solve for the other two by plugging into the equations of the plane. So for the point, what we're going to do is we're going to set z equal to 0. You could set x equal to 0 or y equal to 0. In fact, you could set them equal to whatever you want, but we'll set z equal to 0. And so we plug z equals 0 into the equation of both of the planes. So we get x plus 3y plus 0 equals 2. And then we get 2x minus y plus 0 equals 5. Now we have two equations and two unknowns. We already know z is equal to 0. Let's solve for x and y. And this will give us some point on both. Okay, well, it's just solving a system of equations. So let's multiply the second one by 3. So when we do that, we get 6x minus 3y equals 15. So x plus 3y equals 2. So we get 7x is equal to 17. Why would we give such nasty numbers? We hate to see it. And so x is equal to 17 over 7. And so we solve for y. Actually, I'm sure setting x or y equal to 0 probably would have been easier, but whatever. Doesn't matter. When we solve for y, we get okay, so 17 over 7. So negative 3 over 7 is 3y, so y is negative 1 over 7. And so we get the point. X is 17 over 7. Y is negative 1 over 7. Z is 0. So we get our point and our parallel direction. And so we put these together. I'll just put this in red. So we get 5. Honestly, you could just multiply. Oh, no. Got it backwards. So we get 17 over 7 plus 5t, negative 1 over 7 minus 4t, and then 0 minus 7t, so negative 7t. That is one reason I like to make sure I write a point using the parentheses instead of the triangular brackets when I mean a point, so that it's easy to catch when I'm writing the equation. Because I almost mixed up the two. But yeah, any more questions about this example? Why did you find the cross product? Because we know, so the line lies on both planes. So the line's parallel to the first plane and it's parallel to the second plane. So if you're a vector which is parallel to the first plane, you're orthogonal to the normal vector to that plane. And so we know our direction vector for our line is orthogonal to the first plane, the first normal vector, and orthogonal to the second normal vector. If you want a vector which is orthogonal to two given vectors, you take the cross product. So yeah, we took the cross product of the normal vectors. Probably because they pick a different point. So yeah, they probably picked, wait. (5a) was it? Right. So they probably well, what they did basically was I'm guessing. I'm not sure what process they did, but they probably set one of the things equal to something. So you can actually set any of the variables equal to a number, any number you want, right? So if I set like z equal to 2, so for instance, this is, it gives the point 1, 1, 2. If I set z equal to 2, for instance, what I'm doing is I'm finding the intersection of this line with the plane z equals 2. It's usually easiest just to set one of them equal to 0. But for some reason that didn't work out perfectly here. But this is still a correct answer, right? Remember, there are infinitely many parameterizations, equations for a line, because you can pick any point you want on that line. So in particular, we pick the one with z equals 0. But it's still the same line, even though it's a different equation, if that makes sense. Kind of wish they went through the solutions on this, but yeah. Okay, what else? I probably got enough time for, let's say, a couple more. 9b, okay. Okay. So we want to find the equation of the sphere. Oops. Centered at the point 1, 2, 3, and tangent to the plane z minus 2y equals 4. Okay. So let's draw a picture here to try to figure out how we're going to, well, okay, first of all, let's do this. So we want the equation of a sphere. So for the equation of a sphere, if we know the center and we know the radius of the sphere, we can write the equation of that sphere. So those are the two things we always want to find to define the equation of our sphere. So center is easy in this case. We're given the center. We're not always given the center, as we see in, I believe, part A. No, problem 8, we're not given the center, but we can figure that one out. But here we're indeed given a center. And we need to find the radius now. So what we're going to do is let's draw a picture. So all we know about the sphere is its center. We'll call that the point C. And we know that it is tangent. Let me draw this closer. We know it's tangent to a plane. Let me draw it like this. So what does it mean to be tangent? For a sphere to be tangent to a plane? How many points is the sphere going to touch this plane? Just a single point, right? So here's our sphere. It's going to be tangent. Actually, let me Oh, come on, dude. So here's our sphere. It's tangent to this, let's say this plane right here. And so that means it's going to touch in exactly 1 point. That's a really bad picture. Let me just draw like a 1 and 2 down here. So it's going to touch this plane in exactly 1 point. So that 1 point, if you look at that 1 point lies on the sphere and also on the plane. And what's the relationship between, let's call that our point P. Oh my God. So our point P on the plane. So the vector from C to P, so the line from C to P, the center, and this point on our plane, what's the relationship between that line and the plane? So it kind of looks like it should be the case from this picture. But what's going to be the relationship? They're going to be orthogonal, right? Because if it's not orthogonal, then that means there is in fact some point on the plane which is closer than that guy to the center, meaning it's not actually tangent. So you can make some geometric argument to show that they're tangent, but it's kind of, you can kind of see at a glance when you sort of make a sketch. So we know the vector from the center to whatever this point is going to be orthogonal. So it's going to be parallel to the normal vector. And so what we're doing, what we want to do essentially is we want to find the distance. The radius is going to be the distance from, in fact, this is probably a better way to put it. The radius is going to be the distance from the center to the plane. And the reason that's the case is because it's only tangent at a single point, right? It touches at a single point. That point is going to lie on the sphere. So obviously the distance between C and that point is the radius. And that point also lies on the plane. And so that point on the plane is the closest point to the point C. And so finding the distance between that point and your plane is going to be the radius. So we're going to do the same process that we did when we found the distance between two planes. Almost exactly the same process, except now it's just a point in a plane. So really, we already have a point given to us, C. And so what we're going to do is we're going to find any point we like. Let's call it R on the plane. Look at the vector from C to R, the center to that point. And we're going to project it onto the normal vector because we know that's parallel to CP. And look at the magnitude. Well, that is just going to be the absolute value of the component. Should I give myself more room? So we're going to find any point R on our plane. The distance is going to be the absolute value of the vector from the center to that point R you dot it with the normal vector, and then you divide by the magnitude of the normal vector. And you take the absolute value of the dot product because it could be negative. So this is the component of the projection of the vector from the center to whatever point you found. It's the component of the projection of that onto the normal vector of the plane. So same as the distance between two planes, basically. Okay. So we're given the center is a point 1, 2, 3. Our plane again was z minus 2y. Equals 4. I don't like the way that's written. I'm going to rewrite it, put x, y, and z in order so we don't get mixed up here. So that's negative 2y plus c equals 4. And we need to find a point on this plane. Well, remember the way you can find a point on the plane is you set 2 coordinates equal to 0 and then solve for the third one, or two variables equal to 0. You need to be a little careful here. For instance, we can't set y and z equal to 0 because there's no x which satisfies the equation in that case. But we can set, say, x and y equal to 0. So we get nothing plus minus 2 times 0 plus z equals 4. So we get z is equal to 4. So the point 0, 0, 4 lies on our plane. And so the vector from the center to this point on the plane is going to be negative 1, negative 2, 1. So 0 minus 1, 0 minus 2, 4 minus 3. So the distance from center to our plane, let's remember, the normal vector here is, what is the normal vector of this plane? This plane here. 0, negative 2, 1. So the distance from the center to the plane is going to be absolute value of the vector CR dot in over magnitude of the normal. So negative 1, negative 2, 1 dot 0, negative 2, 1 is going to be 0 plus 4 plus 1, which is 5. Absolute value of 5 is 5. And the magnitude of the normal is going to be root 5. And that's going to be our radius, 5 over root 5, which you can leave like that, but that's the same as 1 over root 5. Whatever, we'll just leave this 5 over root 5. Who cares? Who cares? Literally doesn't matter. And so that's the radius of our sphere. Oops. Okay, so we have a center, we have a radius. So our center is 1, 2, 3. So our equation is x minus 1 squared plus y minus 2 squared plus c minus 3 squared is equal to the radius squared, which is, sorry, not 1 over root 5, it's root 5, Jesus. 5 over root 5 squared, which is just 25 over 5, which is 5. And that's the equation of our sphere. So if it was the xy plane, it would be the same thing. You would do the same process, except your plane would be different, right? What's the equation of the xy plane? Well, that's just the plane z equals 0. And in fact, so this, you could, without doing too much work, we could figure this one out without kind of going through the same process. We could sort of save some time. Okay, so we have the point 1, 2, 3 intersecting the plane z equals 0 at exactly 1 point. Say this is the center 1, 2, 3. Whoops. So it's going to hit the plane z equals 0 and exactly 1 point. And in fact, the sort of the shortcut here is we can find out exactly what that point that it hits it is. You could go through the same process, right? You find any point on the plane z equals 0. That's pretty easy. 0, 0, 0 is on there. And you project the vector from the center to that point onto the normal, and you take the component, or you look at the component of that guy, the absolute value. But we can find out exactly what point this is going to hit z equals 0 at. So we know it's tangent to z equals 0. In fact, just some basic geometric intuition would tell you that the point is going to lie directly below the center, right? So directly below the center means the x and y coordinates aren't going to change, but z is just going to be equal to 0. So this is our point 1, 2, 3. This would just be the point 1, 2, 0. Right. So the normal vector is going to be, or the vector from this point to the center is going to be orthogonal to the plane. So basically, it's going to be orthogonal to 0, 0, 1. Right. So only the z coordinate is going to change. And so in fact, we can just find the distance between those two, which is really easy. It's square root 1 minus 1 squared plus 2 minus 2 squared plus 3 minus 0 squared, which is 3. So that one's relatively simple. You could use geometric intuition and not know this formula. But for the part B, you do have to know the formula to figure that one out. There is another way to do it, but I don't want to spend more time talking about that one. But you could use more geometric intuition and define a line between the center and the plane, and then find out where that line intersects the plane. And then you found the point of intersection, and then you find the distance between the 2 points. You could do that too, but that's a little more involved. But yeah, what else would we like to look at? Number 12. Okay. So R of t is going to be parameterization of a curve. So that's 2 square root t t squared minus t. One plus 3t. So we want to give an equation for the line tangent to the curve at the point 4, 12, 13. Okay. All right, so we're defining the equation of a line, the tangent line in particular. So for the equation of a line, we need, of course, a point, and we need a parallel direction. So a parallel vector. Oops. So our point we're given graciously, 4, 12, 13. So we want the equation of the tangent line, right? So a tangent line to a curve is going to be at a point, is a line through that point parallel to the tangent vector. Right? So our parallel vector is going to be the tangent vector. At our known point, 4, 12, 13 on our curve. In other words, remember the tangent vector is the derivative, right? So it's going to be the derivative at the time t naught. T naught's the thing we got to figure out here, where t naught is the time we're at the point 4, 12, 13. In other words, remember r gives you position. So at the time t naught, when our position is 4, 12, 13. Well, what time t is, what's our time t naught? At what time are we at 4, 12, 13? Right, t equals 4. So we need to find r prime at time t equals 4. So we know our time is 4. So let's take the derivative and then plug in t equals 4. So r prime of t, so we just take the derivative component by component. So 2 root t, when we take the derivative, we get, well, root t is just t to the 1/2. So we get 2t to the negative 1/2, which is 2 over times 1/2, sorry. So we get 1 over root t, basically. We get t to the negative 1/2. T squared minus t, when we take the derivative, we get 2t minus 1. And 1 plus 3t, when we take the derivative, we get 3. So then plugging in t equals 4, we get 1 over square root of 4, which is 1/2. 2 times 4 minus 1, which is 7. And then 3. So we have a point in our direction. And so our line is going to be 4, plus 1/2 t, 12 plus 7t, 13 plus 3t. And that's the equation of our line, our parameterization of our line, rather. Right, so you just need to know that the tangent line is parallel to the tangent vector, which is just the derivative. And so in order to figure out what that is, we need to figure out what our time t is that we're plugging into the derivative. And we get that from the point 4, 12, 13. We find what value of t we're at that point, and then we plug that value of t into the derivative. That's the parallel vector. Yep. What else would we like to look at? Still got some time. I could do a few more questions. So why we plugged in t equals 4. Okay, so we have some curve, r of t, and we want to find the equation of the tangent line. Well, we know it goes through this point here. So the curve through some given point parallel to the tangent line, or the tangent vector. So let's say this is the tangent vector here. Okay, well, the tangent vector, so basically if this is our position, this tangent vector here is going to be r prime. So this is our position at time t, this vector here. The tangent vector is going to be r prime at that same time t. And so what we wanted to do is we need to find out, okay, what time t are we at the point 4, 12, 13? We can find that by looking at our original equation here and solving for t. You could just look at the third component. 1 plus 3t equals 13. Okay, t has to equal 4. Okay, and so our tangent line is going to be parallel to the tangent vector at that same time, t equals 4. And so you just plug that into r prime. Yeah. Number 14, sure. In fact, let me erase this because I think I only get 20 pages here. So let me make sure I can actually do this. Okay, number 14. Okay. Okay, so part A, we want to parameterize the intersection of two surfaces. So we're parameterizing the intersection of y equals x squared and z equals e to the x. Okay. So all right, so there are a couple options here. One is easier to do than the other. In fact, actually, it doesn't really matter here. Okay, so we want to find out parameterization of the intersection of these two guys. All right, remember, I said when we want to parameterize two surfaces, there are like two things that could happen feasibly in a problem that we would give you. So we're going to look at these. Either there's going to be one equation which involves only two variables, and there's going to be a sine-cos relationship between those two variables, right? So it's going to be one variable squared plus another variable squared equals a constant. In that case, you let one be square root of that constant cos and one be square root of that constant sine t. And then you plug those in to solve for the other one in the other equation. Or in one of the equations, you can get one of the variables by themselves. Write it in terms of one other variable. So there's an equation that involves just two variables, and you can get one of the variables by itself. And so what you do is you get that variable by itself, and you let the more complicated guy be variable bt. And then that tells you what the other one is, and then you go to the other one and then plug in here. So we don't have a sine cos relationship here. But what we do have is, in fact, we have two of these equations where we can get one of the variables by themselves, written just in terms of one other variable. So here we can get y by itself, write it in terms of x, we get x squared. And in the other one, we can get z by itself, write it in terms of x, e to the x. And in fact, we'll get the same parameterization, whichever one we choose, so it doesn't matter. So let's just pick the first guy. So for the first one, we can get y by itself. We write it in terms of x. It's graciously already given to us by itself. So we let the complicated guy, x, because it's x squared, bt. And when we do that, we know y is equal to whatever x is squared. So then y has to be t squared. So we take those bits of information, go to the other equation, and then get the third unknown variable by itself, and then plug in these. So z is equal to e to the x. We know x is t, so z is e to the t. So this is a perfectly fine parameterization, but if you wanted to write it in vector form, x would be t, z would be t squared, y would be t squared, z would be e to the t. So that's part A. Are we cool for part A? Okay, so we have this guy. So part B, we want to set up an integral, not solve it, just for the interest of time. So we want to calculate the arc length of this curve of intersection from the point 0, 0, 1 to the point 2, 4 e squared. Okay, so we want to find the arc length of a piece of this. So remember, arc length is going to be the integral. So the arc length from the point you're at time A to the point you're at time B is the integral from A to B of the speed, the magnitude r prime t dt. So there are three things we need here. We need, whoops, we're not given times, we're given points. 0, 0, 1 and 2, 4 e squared. So we need to figure out at what time A are we at 0, 0, 1? At what time B are we at 2, 4 e squared? And what is the speed? What is the magnitude of the derivative of r? Okay. So for what time A can I plug into? Our parameterization is t squared e to the t. What t do I plug in? Right. A is 0, B is 2. right, 0 gives us the point 0, 0, 1. Plug in t equals 2, we get the point 24e squared. So we got the integral from 0 to 2. Now we need to figure out the magnitude r prime t. Well, what is r prime of t? Well, we take the integral component by component. T becomes 1, t squared becomes 2t. E to the t becomes e to the t when we take the derivative. So then the magnitude of r prime of t is the square root of the sum of the components squared. So the square root of 1 squared plus 2t quantity squared, which is 4t squared, plus e to the t squared, which is e to the 2t. Square root of all that, dt. And we wouldn't be able to solve that even if we wanted to using the methods you already know. But all we have to do is set up the integral there. Okay. So then finally, part C, we need to know what is the acceleration of the particle. Oh, wait, huh? Wait, doing 14. Sorry. I was like, wait, no, there was no particle here. Okay. Sorry, part C, curvature. What is the curvature at the point 0, 0, 1 of our curve of intersection? What does curvature mean? Well, there's a formula for curvature. We had a lecture on this. So I would definitely go in and watch that if you don't know what curvature means. So the curvature, remember the formula for curvature at time t. There are a couple formulas, but one is going to be easier to deal with in almost every case. So I would remember this formula if you only want to remember one. It's going to be the magnitude r prime t cross r double prime t divided by magnitude r prime t cubed. So that's a curvature for any time t. But we want to find the curvature at a specific point, 0, 0, 1. So we need to plug in a specific value of t. Well, we already said at the point 0, 0, 1, that's t equals 0 that we're there. So we want to find the curvature at time 0. So what we're going to do is use this formula. So we need r prime of 0, r double prime of 0, take the cross product, and then we can figure it out from there. So remember, I would not take the cross product involving t. I would do it in after plugging in t equals 0. It's going to make your life a lot easier. But you need to make sure to take all the derivatives first before you start plugging in t equals 0. So let's take our derivatives first. We have r prime of t. We said that was, we did that already. That is 1, 2t e to the t. And we also need r double prime of t in our formula, r double prime of 0. So r double prime of t, just take the derivative of r prime. So we get 0, 2, e to the t. Okay, so let's plug in t equals 0 and then take our cross products. So t equals 0, we get our prime of 0 is 1, 0, e to the 0, which is 1. Our double prime of 0 is going to be 0, 2, e to the 0, which is 1. So we're going to need our prime of 0 cross our double prime of 0 in our formula. So that's 1, 0, 1 cross 0, 2, 1. When we do that, we get -2, -1, 2. And so then let's put it all together. The curvature times 0 is going to be the magnitude r prime 0 cross r double prime 0 over the magnitude r prime 0 cubed. Let me make this a little cleaner. So we said r prime 0 does cross r double prime 0 is -2, -1, 2. Take the magnitude, and then we divide by the magnitude r prime 0, and then cube it. So magnitude r prime 0 we said was 0, 1, 0. Sorry, 1, 0, 1. Right? Yes. So the magnitude of -2, -1, 2 is just square root of 4 plus 1 plus 4, which is square root of 9, which is 3. And the magnitude of 1, 0, 1 is square root of 2. Square root of 2 cubed is just 2 to the 3 halves. Why do you do this to me? And that's our curvature. Okay, I will do one more problem. Let's do one more. What would we like to look at? We're all good? 18b, sure. Okay. Let me clear this page. Okay, 18b. So for this, r of t is going to be 2t squared, 3 halves t squared plus 1, and then 5/3 t cubed. Okay, so for part B, we want to calculate okay, I think I see where this is going to go. Calculate the arc length between the points 0, 1, 0 and 2 5/2 5/3. Okay. Yeah, I think I know what they're going to do here. Or the trick for this problem. Okay, so remember, arc length is going to be the interval from time A to time B. We're going to have to figure out what those times are. In this case, of the magnitude of r prime t. It's the integral of the speed from time A to time B. Okay. So what time are we at 0, 1, 0? So at time 0, and then at time t equals 1, we're at 2 5/2 5/3. So from t equals 0 to t equals 2. Okay, so magnitude r prime t. Well, r prime t, it's going to be, so 2t squared becomes 4t. 3/2 t squared plus 1 becomes 3t. 5/3 t cubed becomes 5t squared. And when we take the magnitude, we get square root 4t quantity squared, which is 16t squared, plus 3t quantity squared, which is 9t squared, plus 5t squared quantity squared, which is 25t to the 4. So we're going to simplify this a couple times so we can actually evaluate this. So 16t squared plus 9t squared is 25t squared. So 25t squared plus 25t to the 4. So we can pull out 25 out of the square root. And that is 5. I'll do this one step at a time. So 5t squared plus t to the 4. Okay, so either, a couple things could happen. Either the thing inside is a perfect square, and then you take, you factor it, and then take the square root, and then that just kills off the square root because it was the square root of something squared. And so that's easy to deal with. Is t squared plus t to the 4th a perfect square though? Can we write that as something plus something squared? No, it's not. So really our only other option is to do some kind of u sub. So as it's currently written, we cannot u sub, but what we can do is there something else we can pull out of the square root, right? So t squared plus t to the 4, do they share a common factor? They do, right? That's just t, oh, I hate it, okay. That's just t squared times t squared, or sorry, 1 plus t squared. Right. So when we pull the t squared out of the square root, we just get t. So we get the integral 0 to 1 of 5 times t squared 1 plus t squared. Now we can u sub because we can let 1 plus t squared be u. Then our du is going to be 2t dt. And so we don't have 2t dt, we have 5t dt. So we get 5/2. 5/2 square root of u. And so when we integrate that, square root of u becomes 2/3 u to the 3 halves. So we get 5 halves times 2/3. So we get 5/3, 1 plus t squared. Hang on. From t equals 0 to 1. Oh, sorry, to the 3 halves. And so we get 5/3, 2 to the 3 halves minus 1. So the trick was we had to find a clever way to pull something out of there so we could use sub. And that's basically what's always going to happen. Either it's just going to be a constant, which happens in the case of helices, or it's going to be a perfect square, in which case we can get rid of the square root, or you're going to have to factor inside and pull something out and then use sub. Those are really the only 3 ways we're going to be able to evaluate these guys. Really, only 2 ways. Yeah. Okay, so that is all the time I have for right now. As soon as this becomes available, I will post it on the YouTube. No, you don't need to schedule a time. You just need to go into Canvas during the time you want to take it. And then if it's during that time slot, you go to quizzes and it should be available. And then you just click start. Yeah, but make sure to give yourself an hour. But I'll send out an email with more info in it. Okay, so I'll post this to the YouTube. I'll be holding more office hours. I'm gonna say 6 o'clock tonight. I'll make a Zoom link for that. And you can come and ask me questions if you have more questions about the practice problems or anything else. But if not, I will see you guys on Wednesday. And good luck on your exam tomorrow. All right, have a good one, guys.